think we'll get started. Okay, it's a great pleasure to introduce this morning's speaker, Seraphine Hauser. Seraphine hails from Rottenburg, Germany. Is that correct? I know you went to school there. You're from Rottenburg? And that's in the southwestern part of the country. I've never been there. I'd love to go sometime. And she's currently a PhD student at the Institute for Meteorology and Climate Research at Karlsruhe Institute of Technology, which is often referred to as KIT. I'll even refer to it a couple of times that way. And until this morning, of course, this is not news to Seraphine. I was unaware of the fact that she has a prior connection to this department through Peter Knippertz, who was a postdoc here for a couple of years, and now he's the director of the institute. And Seraphine had an opportunity to work with him as an undergraduate, and then again now as a graduate student, both for the master's and now for the PhD. So that's kind of interesting. And the bachelor's thesis was on the synoptic analysis of dust storms in the spring of 2015 on the Arabian Peninsula. And I remember Peter and I talking about, you know, there was this discussion about how dust can affect the Atlantic hurricane season, and I said, well, because the prior question is, where do the dust storms come from? And we were talking about that in 2003, 2004, and he stayed interested in it apparently. So that was really kind of neat. Sarah's been a world traveler actually during her degree pursuit. She spent 2 months, I think, right at Monash? 3 months with Professor Michael Reeder at Monash University in Melbourne, while she was studying aspects of the problem of the effect of ENSO on rainfall variability in Southeast Australia. And that work was also under the tutelage of Julian Quinting, Christian Grams, and Peter Knippertz again. And that's resulted in a publication in the Quarterly Journal a little more than a year ago. Her visit here over the last couple of weeks, sponsored by the remarkable Waves to Weather program. They seem to have money everywhere, and opportunities for collaboration are just all over the place on that. And it was hosted predominantly by Stephanie Henderson, who can't join us today because she's sick, so that's too bad. She'll be watching it on YouTube. It's really furthered a strong collaboration that I think we were able to establish, even remotely, regarding Sarah's really interesting work on Greenland blocking, among other things, actually. It's not the only part that she's been working on. And its relationship to fundamental physical processes and their interaction with weather regimes and teleconnections. So it's been a great pleasure to meet with Seraphine over these past couple of weeks, and we're currently scheming to ensure that this is not her last visit, and in fact that the next one lasts for a lot longer. So we're trying to make that happen. And this morning she's going to tell us about work directed towards the understanding of Greenland blocking regime life cycle dynamics from the ERA5 reanalysis and also from a potential vorticity perspective. So take it away, Sarah.
So thanks a lot, John, for that introduction. And as you already said, I will give today a seminar talk about one part of my PhD topic with the title Towards the Understanding of Greenland Blocking Regime Life Cycle Dynamics in ERA5 Reanalysis Data from a Potential Vorticity Perspective. So, and I want to start with an introduction to get us kind of all on the same level and start with the definition of atmospheric blocking. And I found this sentence, which I thought would describe this phenomenon quite good, and it says, atmospheric blocking occurs when a jet stream which becomes especially large, and this is what we see kind of here, so I hope that you can all see that this is like Greenland, the US, and the European continent, and this is kind of this large jet stream ridge, and then it forms a separate anticyclonic eddy in the flow, so we see here kind of this high pressure system, how it could look like in a blocked flow configuration, which creates a large-scale persistent weather pattern that blocks the propagation of Rossby waves. And it not only blocks the propagation of Rossby waves, but we also can see here the low-pressure systems in this omega formation. So this shape reminds of the Greek letter omega, where we could like imagine how these low-pressure systems could like be blocked and stay in a longer region than normally. So when we talk about impacts, we can kind of divide them into three different impacts that we see. So we have on one hand, when we think about this blocking high pressure system that stays at a place for quite a long time, in winter we often get cold spells. In summer we often get like these dry, hot conditions with heat waves. But not only in the region where we find a block, also in the region where we find this weather system that kind of cannot get through and stop in their propagation. We can find impacts like heavy flooding events. In terms of predictability, blocking has always been an issue for both, so weather prediction and also like climate models. and especially the blocking frequency over the North Atlantic is still underestimated by most of the climate models. And we see here on the right side a figure that I picked out of a publication from Julian Quinting from my institute and Frederic Vital in 2019, and they were looking at the blocking frequency bias at days 7 to 13 in the Northern Hemisphere, and they were looking at different kind of models that you see here on the side. And what comes immediately is that we see like this underestimation of blocking over Europe and the North Atlantic region. So also, this is a work from Mark Rockwell et al. They found that the misrepresentation of the onset of blocking may be responsible for the largest forecast errors over Europe. So as you see, we need more understanding about atmospheric blocking in general. So today in this talk, I want to talk about Greenland blocking. Why do I talk about Greenland blocking and not like blocking over the North Pacific, for example? One reason for that is that Greenland blocking is shown to last longer than blocking over other regions in the Northern Hemisphere. And also it causes melting events of the Greenland ice sheet by mainly reducing cloud cover, increasing temperatures, and changing the surface energy budget, which can impact global sea level rise. Also, it occurs more frequently in the most recent 2 decades compared to the period of 1980 to 1999. So here again, we need more knowledge on the dynamics of Greenland blocking dynamics in particular. So this is kind of part of my PhD project. So my PhD project is kind of embedded in a collaborative research center called Waste to Weather that John mentioned earlier. And as you see, it's a consortium of different universities. So we have, of course, KIT, because I'm at KIT. Then we have the Ludwig Maximilian University in Munich, and we have the Johannes Gutenberg University in Mainz. So these 3 are the main locations, but also we have contributions from Hamburg, Heidelberg, and also Oberpfaffenhofen. Waste to Weather, so the whole project is divided in 3 parts. We have different research areas. We have research area A that deals with aero growth. We have research area B that focuses more on microphysical processes and cloud processes in general. And research area C that focuses more on extreme weather. And I'm based in project A8 that has the title Dynamics and Predictability of Block Regime in the Atlantic European region. And this is kind of what project A8 looks like. So we have 3 PIs in there, we have 3 postdocs and 2 PhD students, and maybe this face here is familiar to you. So this is Maria, she was here, a PhD student with John together, and also that's not the only connection. We also have Michael Morgan as scientific advisory board member of Waste to Weather.
What is a PI?
It's a project initiator or instructor. So especially for my project, we set kind of goals that I would like to achieve during my PhD. One of the goals is to seek a unified conceptual understanding of the dynamics of atmospheric blocking from a quantitative process-based perspective. Another goal is to investigate the typical evolution of anomalies that are associated with blocking, and of course adopt a local budget framework to quantify the processes governing the life cycles of blocked flow configurations. And the first step during my PhD that I started nearly 3 years ago now was to create a framework where I can get kind of the answers to the questions. And this is not a quasi-Lagrangian potential vorticity framework. I will come back to potential vorticity in the next slide, but just the basic idea of this framework is that we follow anomalies that are associated with the block, and we assign these anomalies to blocking over the North Atlantic European region. And especially in this presentation, the focus is on Greenland blocking. So giving like a short introduction to potential vorticity, it is a product of absolute vorticity and static stability, and it is measured in PBU, so in potential vorticity units. And you can see how such a configuration could look like on the right side. So this is a cross-section. We see here on the y-axis is like the pressure, so like the vertical coordinate, and we have here the range from 25 degree north to 80 degree north, and the gray dashed line you see here is kind of the dynamic tropopause, as it is defined quite often as the 2 PBU contour, and we see that the values below that are smaller than 2 PBU and kind of stand for the tropospheric air mass, and the values above are greater than 2 PBU and kind of resemble the stratosphere. One thing that is special about PB, and maybe also the reason why we use it very often in dynamic metrology, is that is the conservation aspect. So change in PB is only possible by friction or diabatic processes. So we here want to look at arbitrary PB. So this is kind of my basement of my quasi-Lagrangian PB framework. And for that we use era 5 reanalysis data from ECMWF from 1979 to 2021. We mainly use, when we look at PB, model level data with a resolution in temporal of 3 hours and a spatial resolution of 0.5 degree. What we do now is that we do a vertically averaged PB to get rid of like the vertical dimension. So we do a vertically average of PB between 500 and 150 hectopascal, and this is that's something that's not new. That has also been used in a study of Schwirtz et al., where they define a blocking identification index. And on the right side, you see now how anomalies could look like in this region where I'm looking at. So we see here PV anomalies. We see positive ones in the more reddish colors. They kind of resemble troughs or like cyclones. And then we have this big blue blob of negative PV anomalies in the middle. And this is kind of how a blocking anticyclone would look like in a cross section. And if we now think about how the tropopause would look like in this configuration, we see a lowering of the tropopause in the sections where we have positive PV anomalies, and we see a lifting of the tropopause in the region where we see this blocking anticyclone. Just a side remark, because I just forgot it. So anomalies are calculated as deviations from the 30-day running mean climatology. So when we have calculated this vertically averaged PV anomaly, we can kind of get a figure about it and see how it looks like. And the first thing that I did here is to define PV anomaly objects. And for that, I decided not to use a fixed threshold because I'm looking at PV anomalies year-round, and PV anomalies are generally stronger in winter than in summer. So I decided here to use a threshold that varies between minus 0.6 and minus 0.8 PVU, just to make sure that I capture like full anomalies here. So when I have the PV anomaly objects, then I want to create tracks of them to see how their life cycle look like. This is done with a contour overlap tracking that is based like, or it works like you see it here. You have your PV anomaly object, like could be for example that one, and then you look 3 hours after and see if there's another PV anomaly object at that time step that kind of overlaps. So it's kind of a continuation of the track then. A special feature of the contour overlap tracking here is that the algorithm recognizes splitting and merging events that kind of occur quite often and can kind of deal with this splitting and merging. As my title said before, I'm not looking at atmospheric blocking like a lot of people do, just focusing on the blocking anticyclone. I'm looking here at atmospheric blocking from a weather regime perspective, and I just want to take a few minutes to get you more familiar what it means, like to talk about weather regimes. So weather regimes are the most recurrent and persistent states in the atmosphere, and each weather regime is characterized by a specific large-scale atmospheric circulation pattern. That could look like, for example, how you see the screenshot here on the right side. We might have a ridge near Greenland and then a trough over the eastern North Atlantic, and this could be like a circulation pattern that lasts for some days. So it kind of creates such a persistent and also recurrent state of the atmosphere. In the North Atlantic European region, we have kind of a classical definition of the four canonical seasonal regime types, mostly done in the winter time, where we see the two phases of the North Atlantic Oscillation, so the positive and the negative phase. We see a Scandinavian blocking and the Atlantic ridge.
Sarah, can you estimate what fraction of the total winter time is occupied by the collection of these four regimes? So is it 80% of the winter flow looks like this, or is it 50, or, you know?
That's a good question. I would rather say 80 than 50.
Okay.
Yeah. So most studies that look at weather regimes in the North Atlantic European region, they focus mainly on these four canonical seasonal regime types. What is different here is that we use here a year-round weather regime definition in this region that is mainly by Karlsruhe, so from a supervisor Christian, and it basically works like that. We have 10-day low-pass filtered 500 hectopascal geopotential height anomalies. They get normalized, and then we perform a EOF analysis in the North Atlantic European region, and then do a key means clustering with the leading 7 EOFs. And this all results in 7 year-round weather regimes that we get. These are shown here on the right side. So you see all the 7 weather regimes, including on the bottom the no regime, which kind of is the state when none of the other weather regimes is active. And in shading you see geopotential height anomalies, and the black lines, black solid lines shows us the geopotential height, so the absolute values. And we can see that these 7 regimes kind of divide into categories. So we have 3 cyclonic regimes, the Atlantic trough, the zonal regime, and the Scandinavian trough. You will see that most of these 3 regimes are dominated by this negative PV anomaly. And then we have the 4 anticyclonic regimes, the Atlantic ridge, the European blocking, the Scandinavian blocking, and the Greenland blocking. And these are the 3 that we see here. And these are dominated by more the anticyclonic anomalies. And as I said, we are looking here at Greenland blocking, which is an anticyclonic regime. So now you have kind of an idea what weather regimes are, but we want to use here weather regime life cycles. So I want to get you a bit more familiar with life cycles. And before that, I just want to have a look at a Greenland blocking in general, how like the composite for all the times where we have this regime active looks like. And this is shown here. So in shading, we see a geopotential height anomalies at 500 hectopascal, and we see here over Greenland this really large and strong anticyclonic anomaly in terms of a positive geopotential height anomaly. Down to the south, we see more this negative negative geopotential height anomaly. And when we now switch to the PV perspective and use here the upper level PV anomalies, we show them here in this dashed and also the solid lines, so the solid red lines here point to positive upper level PV anomalies and the dashed white ones to negative upper level PV anomalies. And we kind of see how it fits together, this perspective changing from geopotential height to PV, and it kind of gives us like a thumb up. You can do like the change to PV here. So when we now want to look at weather regime life cycles, we use the definition from the weather regime index. This is work done by Michel and Rivière, and its basic idea behind that is that we use a normalized projection of the low-pass filtered Z500 anomaly pattern, so the actual one, to this like mean regime pattern. So it kind of describes how similar is my actual circulation pattern compared to like this mean regime pattern that we see here. And then we get kind of a timeline that you see here. So on the y-axis we have the weather regime index, on the x-axis we have the time, and then this blue line shows the weather regime index, for example, here for Greenland blocking. And whenever the curve kind of hits the 1 here, it kind of shows an active regime life cycle. And when like this period of values greater than 1 is larger than 5 days, then we have an active regime life cycle. And we can kind of define the onset date and the decay date of the weather regime life cycles. But the next question is now, okay, we have the regime life cycles, we have the tracks of negative upper level PV anomalies, but how do we match them now? And this is done by defining a regime mask. The regime mask is basically the region enclosed by the minus 0.3 PBU contour, and it's shown here in this blue contour line. So whenever there is a negative upper tropospheric PV anomaly that overlaps at least 10% of this regime mass during an active regime life cycle, the PV is assigned to this regime life cycle, and it's called like the contributing PV anomaly. So just to give you like a summary now, so the quasi-Lagrangian potential vorticity framework consists as the first part of the identification of upper tropospheric negative PV anomalies and kind of objects. We are tracking these anomalies based on the contour overlap, and we assign PV anomaly tracks to active Greenland blocking regime life cycles by the spatial overlap with this climatological regime mask. And we now use this framework and apply it to Greenland blocking. So this is part, like my results part in this talk, and it is split into split in three different parts. So first, I want to give you like basic information on Greenland blocking regime life cycles. Then I switch to contributing negative tropospheric PV anomalies, and then I will show you the pathways of PV anomalies, so kind of where do the PV anomalies come from before they reach the Greenland blocking region. So first of all, a bit of data and kind of how large my sample size is. So we look here at era 5 data from 1979 to 2021, and we have in total 177 regime life cycles. And when we look in the different seasons, we also see that it's not like equally distributed. So we have less regime life cycle in DJF, and the majority is located in March, April, May. So it is kind of interesting to now look more at the life cycle lengths, because all these Greenland blocking life cycles, they are not like equal in length. And this is shown here. So on the y-axis we have the life cycle length in days, and on the x-axis we have the seasons, and also get like the year-round that includes all the life cycles. And we basically see, so I don't want to go into detail here, but we see that we have longer life cycles definitely in DJF compared to the other seasons. And if we kind of compare this now with the other regimes, so this is now the frequency in terms of how many days in a season is a specific regime active. We see that there's kind of a decline in DJF, but it's not as huge as we would expect. So we have less life cycles in winter than in other seasons, but therefore we have longer life cycles in winter than in other seasons, which is a quite interesting aspect here. Then switching to my second part, I want to give you some more information about these contributing negative tropospheric PV anomalies. The first question that we could ask here is, what is the mean percentage overlap of negative PV anomalies with the regime mass? So what is the share of the area of this negative PV anomaly that we see here in this regime mass that is shown as this blue thick contour? So we can do this now for different seasons and do this kind of as a composite left to the Greenland blocking onset, because this is like the time where we can center all the regime life cycles independent of how long their regime life cycles are. So you see here on the x-axis the time lag to the onset in hours, so it spans the period from -80 to +80, and on the y-axis we have the percentage overlap of PV anomalies in general with the regime mass. And what we see for different seasons, and I put here in 2 lines for each season, so we have one that is called like the running one, which is the running threshold that I'm also using now at the moment, but we also could look at this analysis where we would have chosen like a fixed threshold, just to make you aware of a few things. So all lines that you see here, they show like this increase in the overlap just prior to the onset. So we see that kind of prior to the onset of Greenland blocking, we don't have like a lot of negative PV anomalies in this region. They seem to come into this region just prior to the onset. And also we see like the decline is really different in different seasons, with like a longer overlap, for example, for the winter terms on DJF, so the blue curve. But we also see differences when we look at the different thresholds. So if we use a fixed threshold or if we use a running threshold. And what comes here in our mind is that when we would use like a fixed threshold, we would get a really small overlap in general of PV anomalies in the summer. So when we use now this running threshold and use a lower threshold, we get kind of closer in terms of the overlap here. So the question is, so the next question is it only one PV anomaly that contributes to a Greenland blocking regime life cycle, or could it also be that we have several PV anomalies that contribute? And this is shown in this figure. So here I just took all the regime life cycles that I have for Greenland blocking and counted the number of PV anomalies that overlap with this regime mass that I showed several times. So here on the y-axis you see the number of PV anomalies that contribute to a life cycle, and here we see the different seasons. And you can see very quickly that it's not just one PV anomaly that contributes, and there's also a really high variability in the number that ranges from 1 to 11. So this seems to be a really complex situations here, so we ask ourselves, can we find categories to reduce the high variability in the number of PV anomalies? And for that I try to find different categories, so this is now more a subjective analysis that I did here, and it's just based again on the regime mass that you see here in blue, and then I just look for each life cycle how many PV anomalies contribute, and do I see like a specific pattern. And one of the pattern, and this is definitely the most easy case, is if we have just one PV anomaly. So we have here on the y-axis the overlap with the regime mass, and on the x-axis the time. So in this configuration we would have just one PV anomaly. It kind of comes into the region, stays there, is persistent and quasi-stationary, and then just moves maybe out of the region again after the block is kind of breakdown. The second category is when we have multiple contributions. So we have more than one PV anomaly, but we still are able to determine like one main contributing PV anomaly, and this is the second category. The third one is called like the transient behavior, because here we see PV anomalies that come into the region, kind of propagate out again, and then another one pops up, and then the next one pops up. So we have like this transient behavior in this category. And the fourth, and this is not really a surprise, we also have like the complex category, where all the cases fall in there, really complicated, and where we have a high number of PV anomalies that contribute. And there it also gets really hard to determine, okay, this might be like the most important or the main PV anomaly. We can now look at the distribution of these different categories for different seasons. And I just want to highlight here three things. So one is that we find a lot of life cycles that fall into this complex category are found in summer. So this is one remarkable thing that we should keep in mind, and which might be also quite important when we further look at the analysis of Greenland blocking life cycles in summer. Then the transient behavior occurs quite often in DJF, so in the winter months. We have this multiple contribution category mostly in summer again, and then we have the single contribution quite often in spring. So you see there are seasonal differences. So still we did not get like rid of all the multiple PV anomalies, and it makes it really hard for analysis if you have a life cycle that has just one PV anomaly, and then you have a life cycle that has 11 PV anomalies. So the question here is how to handle all regime life cycles, although they are all very different in the number of contributing PV anomalies. So I decided here to define a main PV anomaly. So the PV anomaly track that has the most frequently the highest overlap with the Greenland blocking regime mass during the active regime life cycle is kind of determined as the main PV anomaly. And in most cases, this is also the global maximum in the overlap during the regime life cycle. So if we would have like here a life cycle where we have 3 contributing PV anomalies, we would select in this case this PV anomaly because it shows for the longest time the highest overlap with the regime mass. So in the next step, we want to look at select PV anomaly frequency, because this gives us now an idea where we find these PV anomalies in general. And this is shown here. So we see here in shading the normalized frequency, like the spatial frequency of the main contributing PV anomalies linked to the Greenland blocking regime onset. And this is now for 2 days prior to the onset. What we see here is just like a huge band of high frequency. But if we now go back in time, and this is for -3 days, you kind of see that there seems to be like 2 centers of action. So one is located more in this region, and the other one more over the eastern North Atlantic. We can go further back to -4 days, and we see that this even splits more into 2 like clusters. So we have one here over the eastern US and one over the eastern North Atlantic, and it's no surprise that when we even go further back in time to -5 days, it separates even more. So we find two regions with enhanced occurrence frequency of main PV anomalies a few days before the onset. So in the next step, we decided to determine the center of mass of all these PV anomalies, and these are shown in the dots that you see here. And then we did key-means clustering at the time of -3 days prior to the Greenland onset, and came up with these two categories. So the first one, and these are more the yellow dots that you see here, is the now called retrogression cluster. It includes all main PV anomalies that reach the blocking region from the southeast and eastern part. And then we have a second pathway, which is called the upstream cluster. And here the main PV anomalies reach the blocking region more from the southwest and the west. And we have a third category. I won't go into detail too much in this talk, but these, there are the PV anomalies that develop quite late, and they do not exist at the time of the clustering. So we have PV anomalies that are not developed already at this time when we perform the clustering. What we can now do for the two first categories and pathways that are shown for the retrogression and upstream cluster is to show you a bit the characteristics and how they differ. So we see here the PV anomaly area on the y-axis, and this is now the time like from -10 days to +10 days around the Greenland blocking onset. And we see really clearly that for the retrogression anomalies, which is the red line, we see that these anomalies are larger in area than upstream anomalies in the mean. We can then look at the longitude position and see also a bit like the propagation of these anomalies. And we see again here, so again we have time like from -10 to +10 days. And here at the longitude position, we have here 0 degree, and we have here 80 west. And we see like this clear eastward propagation of the upstream cluster anomalies here just prior to the onset, and then also this westward propagation of the retrogression cluster anomalies. So this kind of shows us again that there are really two pathways. Then we could look at the latitude position of the center of mass of these PV anomalies and also find remarkable differences. So the upstream anomalies, they propagate towards the northeast just prior to the onset, so that's the time that you see here, while the retrograde anomalies, they reach the high latitudes much earlier and are already at this latitude during the onset. This is also like a difference. And last but not least, we can also have a look at the PV anomaly amplitude, how it develops with time, and just make sure we're looking here at negative PV anomalies, so the lower you go, the stronger these PV anomalies are. And we see here that the upstream anomalies, they amplify the strongest just prior, so again here in this period, and after the onset, while the retrograde anomalies experience their strongest amplification already earlier. We can also now look at the seasonal occurrences of these pathways, and we see that in most seasons, so in March, April, May, June, July, and September, October, November, we see that the upstream pathways kind of dominates in all of these seasons, but except from DJF, where we see that the pathways are kind of equally distributed. So this is really different. This is really interesting, and this is also something that will come later in my outlook. A question here that we also ask is, can we find seasonal differences in the lifetime of the main PV anomalies, just relative to the pathways that we see? And is there also like a connection in the PV anomaly lifetime and the pathway? So this is what you see here. This is the lifetime of the main PV anomaly. So it just shows you like the length of the track in general of the contributing PV anomalies. So we have here on the y-axis the life cycle length in days, and we have here the different clusters and also the different seasons. So we see it here for DJF, MAM, JJA, SON, and each box plot represents here a cluster. So the red one is the retrogression, the green one the upstream, and the gray one the residual cluster. And what we see here is that the PV anomalies from upstream, they have a shorter lifetime than the PV anomalies that propagate retrograde from Europe, which is quite remarkable. Also, when we look at PV anomalies in the residual clusters, they show in comparison to the other two, so in comparison to the retrogression and the upstream cluster, a much shorter lifetime, which is also quite interesting. And then as a next step, we can also look at kind of the timing of the PV anomaly development. So when does the PV anomaly develop relative to the Greenland blocking onset? And this is shown here. So we have here on the y-axis the timing, and positive means that the PV anomaly develops prior to the Greenland blocking onset. And if the values are negative, so this in this region here, it means that the PV anomalies, so the main PV anomalies, they kind of develop after the Greenland blocking onset. So we see here that the PV anomalies that following the retrograde pathway, so in the red boxes, they tend to develop earlier than the PV anomalies from upstream. And the PV anomalies in the residual cluster, they develop shortly prior, during, or even after the onset of the Greenland blocking. So there is some kind of a question where we ask, is there a relationship between the pathways and the specific sequence of regime transitions prior to the Greenland blocking onset? And this is where we look at the weather regime index again that I introduced you like a few slides before, and do also like a legged composite analysis. So this is again the time around the Greenland blocking onsets in days, so ranging from -10 to +10 days. We have here the weather regime index on the y-axis. The solid lines show the retrogression cluster, and the dashed ones the upstream cluster, and the different colors point to the different 7 weather regimes that we see. And what is kind of remarkable here when we look especially at the retrogression cluster is that we see kind of a sequence of a regime of weather regimes just prior to the Greenland blocking onset, where we see here in green this European blocking, and then in yellow this Atlantic ridge, and then finally the Greenland blocking, which gives us kind of a hint that there might be like a retrogression of the PV anomaly towards Greenland that already contributed maybe to a European blocking or to an Atlantic ridge. And with that, I'm coming to my summary of the talk. So we developed here a quasi-Lagrangian potential vorticity framework that matches anticyclonic PV anomalies to Greenland blocking regime life cycles. And we found that the main contributing anticyclonic PV anomaly is determined, and composite analysis and during clustering, we find 3 different pathways of PV anomalies to the Greenland blocking region, which is the retrogression one, the upstream one, and the rest cluster. Also, we find distinct differences in the characteristics of PV anomaly tracks and the temporal evolution of PV anomaly properties in general. And in most seasons, we saw that we have a lot of this upstream pathway, but DJF stands out. And this is also like the perfect time to come to my outlook, and of course the ongoing collaboration with John and Steph here, where we want to get more insights into the dynamics of each pathway with focus on DJF. And especially with Stephanie, I'm working on the effect of remote effects of El Niño and also the MJO. And more with John, I will work on the role of extratropical cyclones and the jet stream, and also hopefully get more insights into the processes that happen into this in this rest cluster. And with that, I'm at the end of my presentation. Thanks a lot for your attention, and if you have any comments, questions, I'm happy to discuss them.
You might have said this, I maybe just missed it, but how did you decide when the point of onset for the regime was? Like, was it like when they overlapped, like the PV anomaly and the ridge overlapped, or when it propagated over Greenland?
It's kind of hidden in the weather regime definition already. So there's the weather regime index that we use to kind of determine these life cycles. And life cycles mean that we have the onset and the decay to just say, okay, that's the period now. And we get the onset when we see that this weather regime index in this timeline first like hits the 1 mark. So
Okay, so it's when they intersect.
yeah, it's just like a threshold that we set, and then we say, okay, whenever this is like, whenever we meet this criteria, then yeah, just the life cycle starts.
Okay.
And it's the same also with the decay date. So the decay date is also when the line it's decreasing again. Yes.
Taking a few slides from here, you had your analysis where you were showing the different types of whether it's one trackable anomaly or multiple. Yeah. So I noticed here that the time axis is the bottom, correct?
Yeah.
So do you find that these different types have different timelines, and that if you are able to reinforce a primary PV anomaly, does it last longer?
That's a good question. I haven't looked at this in particular, but I think that you will not find a clear signal. So there are. So when I started my PhD and found that we have multiple PV anomalies that contribute, for me it was kind of okay. These PV anomalies. So when I have a sequence of PV anomalies, they kind of feed the existing block or kind of make sure that the life cycle stays for longer. But we also see life cycles that have just one main PV anomaly and they're super long. So I would not say that we see like a preferred life cycle length in these for subjective categories.
Cool, thank you.
From this same slide, what would happen if you had a single PV anomaly and that broke apart? How would your algorithm keep track of that? Would that still be one contribution, or would it be counted as another PV anomaly?
That is kind of, I just put that in the presentation, but that is kind of what you see here. So that would look like here. So if you have a breakdown of a PV anomaly and it breaks into two parts, the algorithm will first detect, okay, which is like the PV anomaly where I will kind of continue my track, and which is the one that's split it apart from that. If they both has like an overlap with the regime mass, they will both appear here. But the tracking, from the tracking, I get the information, okay, but that PV anomaly that splits up is original from another one. So that's kind of the advantage of the algorithm that detects splitting and merging.
Nice, thank you.
Yes?
Hi. What do you think are the physical origins of the PV anomaly? What creates low potential vorticity other than tropical air? Is that basically where they come from, or is there some physical process that's creating it?
I've started to look at this in general. I did not include that into the presentation because then I would have to give like a talk for 2 hours, I think. But there are definitely differences in the three pathways that we find. And I think that like latent heating in general plays a huge role, especially maybe not that much in the retrogression cluster, but definitely in this rest cluster where we see, I mean, I just can kind of tell you a bit what I discussed with John so far. So for the rest cluster, we often see like a jet streak just prior to the Greenland Blocking onset over the eastern US coast, and we see like extratropical cyclones that develop really fast, and they kind of might be associated with latent heat release and creating like this.
I've been looking at what I call tropical plumes at upper levels. And the plumes bring with them very low PV anomalies that are created in the upper level, basically the TTL of the tropics and the UTLS to some extent. And so 500 millibars is a little low to me looking at this, but I find that these anomalies tend to push polar.
Okay. Yep.
And behind them is an arched, or in front of them is an arched subtropical jet stream. So the subtropical jet stream would be more a manifestation of this plume pushing polar, but it carries with it very low potential vorticity, near zero.
Yep.
And so that's the thing. Potential vorticity is highly conserved, and there's not a great. There must be some obvious source of the low potential vorticity, which I would think is the tropics.
Yeah. Yeah.
Yeah, when we were looking at some of those sources, it was clear that you had these poleward plumes going up either west of Greenland, well west of Greenland, or well east of it in some cases. I mean, they were almost always tied with the big extratropical development. That was only December, January, February that we were looking at together during the visit. So there were times with really strong cyclogens.
But the extratropical development itself benefits from low PV aloft.
Oh, yeah.
Because, you know, it brings in the higher PV from the west, but
Yeah.
the lower PV aloft enhances the ability for it to overturn the process
Yeah.
to occur and develop divergence fields,
Yeah.
which releases the cold air. So these things bomb out in the presence of a relationship between low and high potential vorticity
Yeah.
that would occur. But I, you know, we typically see these low plumes coming up, but you can also produce low potential vorticity areas from convective, deep convective processes.
Yeah.
If they get deep enough.
Yeah. Thank you.
Oh, Ian.
Yeah, I had just a question on a similar thread. You had several different slides that depict the differences between the retrograding and the progressive ones. The final slide of that, I think, was an amplification showing that they amplified differently. And I was wondering if did you find that amplification was something non-conservative, or is it merely that I'm able to bring low PV to a higher latitude where it appears more anomalous?
Mm-hmm. I have looked a bit into the dynamics of these anomalies, split it into these two categories, so the upstream and the retrogression pathway. And what I find is that when we look at the upstream anomalies, they are highly amplified just prior to the Greenland Blocking onset. And this amplification is mostly due to latent heat release and the divergent outflow that we see. And this is something that we do not see, or just a tiny bit in the retrogression anomalies. And I think this is also something that we will have a look further on, because we have the feeling that these retrogression anomalies that we see, they already contributed to another blocking over the European continent, and they are already like large in area. I mean, that's what we also saw here, that they are large in area, and so they kind of retrograde towards Greenland, and they are already strong in their PV anomaly amplitude strength. So, yeah.
Do you see the difference as being purely like a spatiotemporal difference between when the Rossby wave packet breaks, like it's retrograding into Greenland, it's the wave train over the Atlantic had a cyclone family, and then it broke over Europe? Or are they actually distinct, different? Does that make sense? I'm just picturing two Rossby wave packets moving across some latitude line, and in one case, the cyclone family is housed over the U.S., and in the other one, the cyclone family is housed over the Atlantic, and so the Rossby wave breaks in two different locations.
Yeah, I mean, that's a good point. I haven't done a lot of analysis on that, but that's definitely something that could be quickly to check that. Yeah.
Oh, is there somebody back there? I don't know. I'm trying to wait. I had a couple of questions. One is related to this conversation we're having about the amplification of these anomalies. I was fiddling around with the mathematics, and I might have it wrong, but is one of the other ways you can have amplification of a PV anomaly to have the perturbation wind act on the mean PV gradient in a way that pumps it up or down in terms of its value?
Yeah.
And are there any systematic connections, to other types of physical processes that lead to, the perturbation wind cutting across the climatological contours in one direction or another, that you can relate to weather systems or to weather regimes?
Mm-hmm. Definitely. So one part of my PhD that I'm already working on is to look more at piecewise PV tendencies, to just get like a budget of the whole development of the PV anomalies, where we can really split the processes into dry and moist dynamics and see how like shared it is and how important like dry and moist dynamics are. But this is just like ongoing work, so I don't have like a lot of results for that already here. But I hope that we get more insights if we look at these processes, not only in terms of a budget that we do, but also like in a spatial composite to see where these processes are.
Okay, yeah, and I think you've conveyed your instinct a couple of times today, which is that the retrogression cases are going to have substantially less impact from latent heat release than the upstream ones and the res cases. I agree with that. The other thing I noticed, I can't remember which exact slide it was on, it's one where you had a lot of the colored bar graphs, maybe the last one that you showed. I think it had to do with length of time before the, yeah, this one right here, June, July, August. That upstream anomaly timing is interesting because it makes me wonder if it's not what we call here in the central U.S., right on the border with Canada, is the so-called ring of fire in June and July, where we have a giant anticyclone that's almost stationary, and on its poleward edge, because the inertial stability is so low, it's constantly firing off convective activity, which only furthers the block there. And I wonder if that isn't one of the giant June, July, August blocks that works as an upstream precursor to a Greenland block, though they're not so strong and so common in the summertime. But when they do happen, I wonder how many of them have ring of fire predecessors. It
Yeah.
never occurred to me until you showed this.
Yeah. Yeah,
That could be really interesting. You know, MCSs over southern Canada and over the Midwest might be a T-minus 5-day precursor to a Greenland block in the summertime,
Oh, okay, yeah,
which could be kind of cool to see.
yeah. That would be interesting.
Yeah.
Look at that.
Any other questions? Ian?
Yeah, I guess on the same train, so the PV anomalies obviously can be tracked in this flow following framework, but the analysis area is certainly a set. It's an Eulerian sort of perspective. So I guess I'm wondering, just intuitively, how do you think of the life cycles of the blocks? You know, as when do you call it a Greenland block? Is it when it's built and then you're expecting it to move to Greenland, or it's built over Europe and it's expect to retrograde over, and then in the decay stage, is it should I think of the block as falling apart and the flow going back to zonal, or does the block live on and just get moved somewhere else?
So, as an answer to more your first question, I mean, it's still like this weather regime perspective. So, I think I mentioned it also in the slide where I introduced you to the weather regime index. This index is more like designed to find like, okay, I have like my actual circulation pattern at a specific time, and then I see, is it similar to a Greenland blocking? Is it similar to Atlantic ridge? Is it more similar to like the zonal regime? And this is kind of how this weather regime index is in general designed. So if we have like this onset date here, I think that I said it to John multiple times the last weeks. It does not mean that at this point of the onset, the Greenland block is already established. It's just like a build-up of the whole regime. And same also with the decay. Decay is not necessarily the time when the block kind of dissipates. It's just a time where the regime ends, where the regime, like when the circulation at that point is not anymore similar or does not show any similarities anymore, not like strong similarities to this pattern.
Yeah.
So whenever like the block is at some point moving them towards Europe, for example, and its breakdown, it might be more similar to, for example, the Scandinavian blocking. So this is kind of how you have to think about regime life cycles in this configuration.
Because you have similar masks for the Scandinavian block, so you could actually have an anomaly progress from the Greenland block mask into the Scandinavian block
Yeah.
mask. And it's the same anomaly, but it's not the same weather regime anymore.
Right.
Yeah, by definition. Okay. Any other questions for Seraphine? Oh, Anker.
Sure. This is more out there, as I don't tend to think a lot about TV anomalies across the Atlantic. It's really cool stuff. I'm just kind of curious more from a surface person. You know, Greenland's a pretty high altitude chunk of ice, high albedo. Does the presence or absence of Greenland itself have any factor in this type of analysis? I know you can't necessarily say because you can't remove Greenland from your
Yeah.
analysis. I'm just kind of curious if that's kind of part of the thinking or not, if there is kind of a land atmosphere interaction at all.
Yeah. I mean, I have no idea. I think that was something that is still on my to-do list to look at the role of topography in general in Greenland and the effect. I mean, also in terms of of cyclones and their kind of tracks. It could be really interesting. So I haven't looked at that stage, but it's super interesting. Yeah.
Curious. Thanks.
As a proxy for getting rid of Greenland, we were trying to buy it a couple of years ago, as you might recall. So, any other questions? Okay, let's thank Seraphine one more time.